And we're back with Kirchhoffs Second Law, but this time we have some numbers to play around with.
The circuit is the same as in the previous video. It has the same components, the same starting point, the same mesh and the same direction, but we have some specific values for the components. For example, we have the source voltages, 9 volts and 16 volts respectively. We have the resistance values of the resistors. R2 is 2 ohms and R3 is 5 ohms. And we also know the current that flows through the subcircuit, and that current is 0.7 amps. And the direction of current coincides with the clockwise direction of the mesh. So we're given these values and we're looking for U1, the voltage drop across the resistor R1, as well as the resistance value of R1 itself. And to find out these values, we need to set up the equation for Kirchhoffs Second Law and to solve that equation for the values that we're looking for. So, do you remember how to set up the equation that reflects Kirchhoffs Second Law? The general expression is the sum of all voltages or voltage drops, and that's included in UI, is equal to 0. That's the general formula. And do you also remember how to specifically set up the equation for our circuit? If we have a starting point, and by the way, it doesn't matter where you put the starting point, because one way or the other, you will reach the starting point back. And the math works out regardless of where you place your starting point. For convenience, we're going to use the same starting point as in the previous video. So, beginning at the starting point and going in the direction as indicated here, if you encounter a resistor, you treat the voltage drop across the resistor as negative, therefore minus U2. And this time, I'm not gonna write down the symbols of the voltage drops. I will directly write down the voltage drops expressed as R, in this case R2, times I. The product of the resistance and the current is the voltage drop across the resistor. So minus R2 times I plus US2, and that was plus because the negative pole comes first and then the positive pole, and then minus R3 times I minus US1, minus because the positive pole is on our way first, and then the negative pole, and we have this resistor minus R1 times I, and that must be equal to 0. So I'm gonna rearrange this equation into R1 times I, because R1 is the variable that we are looking for that we don't know yet. I'm gonna try to be quick. R1 times I is equal to minus R2 times I plus US2 minus R3 times I and minus US1. And now we can plug in the values. So R1, actually what I'm gonna do, I'm gonna divide the right side by I and I is known as 0.7 amps. So I'm gonna open up a bracket, and I'm gonna write down R2 is 2 ohm, so minus 2 ohm times 0.7 amps, and the product of a resistance and a current is the voltage, plus US2, which is 16 volts, minus R3. R3 is 5 ohm, times 0.7 amps, minus US1, which is 9 volts. And I'm gonna divide this whole term by the current, which is 0.7 amps. Okay. Let me find the products inside this term. So minus 2 times 0.7 is minus 1.4 volts. I can write down the direct unit volts, plus 16 volts minus 3.5 volts minus 9 volts. And that thing divided by 0.7 amps. Okay, minus 1.4 plus 16 is going to be minus 14.6, and then sorry, it's going to be 14.6 positive, and then minus 3.5 is going to be 11.1, and 11.1 minus 9 is 2.1 volts. Divided by 0.7 amps, and that gives us R1 is equal to 3 ohm. Dividing 2.1 by 0.7 gives us a whole number. So the resistance of this resistor is 3 ohms, and computing the voltage drop across that resistor is an easy task. You just multiply R1 by the current. That gives you 3 ohms times 0.7 amps, and that is equal to 2.1 volts. So basically, the same value that you have already seen here. Well, and this is how you apply Kirchhoffs' second law to find unknown resistances and unknown voltage drops in your circuit or DC sub-circuit. And this is just one aspect, or this is just one of the two Kirchhoffs laws. If you combine these two laws, then you're able to solve more complex DC circuits where you have several of sub-circuits that look like this. And we will of course cover some examples on how to compute voltages and resistances in a more complex circuit where you have to use both of these laws.
But for now, I hope that this video was helpful to you, and I hope to see you again.